Hello, today I'm gonna talk about cyclic group and isomorphism. I assume that you already know what is cyclic group and what is isomorphism. The final goal of today's lecture is to understand this sentence. If the order of cyclic group is n finitely, then the cyclic group generated by X is equal to mu sub n up to isomorphism. Also, if the order of cyclic group is infinite, then the subgroup generated by X is equal to integer set up to isomorphism. Okay? To understand what is order, we have to understand what is order. Order of some element in group is defined by this. The cardinal number. This means cardinal number, right? Cardinal number of subgroup generated by X. This is the definition of order of X, right? And we have to understand deeply about X. So we can write the subgroup generated by X like this. Like use X alphabet, and these all of elements are, we say, called word, right? So write more precisely than like this. If the order of X is n finite, then this cyclic group must terminate when here. This must be 1. Actually, the order of X means n is the smallest natural number such that makes X identity exponentially. I think almost will prove only this part, so I want to take this part in this video because this is my channel, and I guess somebody have some difficult to prove here. This part is very trivial, but there is something difficult to prove rigorously. Well, now I focus on to see this structure. Okay, let's see. I write as many as elements, right? If x and x to the power of 3 is equal, then identity is equal to x to power 2 x square, right? So the important thing, the essence is just the interval of the cycle, and there is no origin. If these two are same, then x and x3 square is same, and x to the x square and x to the power of 4 is same, and this is same, then this is same, like this. There's no origin, so we can focus on the partner of 1, right? And we have to so that's clear, right? If the order of this set is n, then x to the power of n minus 1 must be same. Then there are overlapped, and we can banish this element. This is very trivial if we consider the structure of this set. And now I want to talk about this part. I think this isn't trivial, but very easy. Write this cyclic group generated by X, then we already know that the cyclic group is this, and now we assume this premise. We just have to prove there is no overlapped element, right? Then the order of X is n, right? So we have to just prove there is no overlapped element, and I will use reduction to absurdity. If let's assume that there is some index I and j such that x to the power of I is equal to x to the power of j, then the index must be in 0 and n, right? This is very easy. Then j minus I is smaller than n, but also x to the power of j minus I is identity. So this is contradiction to our premise such that n is the smallest natural number. J minus I is smaller, but also makes x identity, right? So I want to emphasize our philosophy. If the order of x is n, if and only if n is the smallest natural number such that x to the power of n is equal to identity. Also, if any of the necessary or enough condition, the cyclic group generated by X can be written as this. This is very simple construction. Or more pentatically, we can define order of X more easily. Maybe someone think this is more difficult, but this is more easy and more mathematically. So choose the x. This x is this x, and define this function called gamma sub x is just the exponential function. Then this function of kernel is subgroup of the integer, right? This is always true, and so there is very important fact we already have to know, that is the integers subgroups are only nz. This is very important in abstract algebra construction. So this kernel of R gamma sub x must be nz, and we call this n order. This is the same definition because the kernel of gamma sub x makes x identity, right? And this is the one of the definition of order, right? And this n is the smallest one of a set of a, right? So this is more pendatic definition, and I suggest be friendly about this sentence. Oops. Before the next subject, I have to fill the gap of this equality. Why subgroup of integer have to the form of nz? I'll use division algorithm to prove this lemma. Let's write h to indicate subgroup of integer. If has only identity, then clear, because we can write and its identity. This is identity. But if h isn't zero group, then there must exist positive number in h, because if there exists negative number, then the inverse of n must be there. So we can choose the positive number, and I want to claim that the smallest n among the above satisfy h is equal to nz. If we choose some element in h, then we can use division algorithm, and a is equal to q and plus r, and r must inside between 0 and n, the division, right? The divisor, right? Then the a is must in h, and also n is in h, so qn is in h, so r is in h, right? But r is smaller than n, so this is contradiction to the assumption of n, so we can conclude that r is 0, and so n divide a. So this is the proof of lemma. So I finished about definition of order. Let's return to our origin, this sentence. Now we can prove this sentence. The first sentence, this is proof. This phi is isomorphism. Very easy, right? Because the group and mu sub n has same cardinality, so this phi is bijective very trivially, and also this phi retain the construction of each group. The both two have multiplicative algebraic structure, so very trivial. And also when order of x is finite, the cyclic group and integer have same cardinality, right? And so bijective is very trivial, and we already know that this function is like log or exponential kind of, right? And this log and exponential preserve the algebraic structure between the multiplicative and additive. So this is the proof of second sentence. So this is the final subject, and this is our course. Let's understand this exercise. The subgroup of cyclic group is always cyclic group. But this is very simple question because the power of isomorphism. Any group is any cyclic group is equal to integer or mu sub n up to isomorphism, right? So we have to just think the case when integer and mu sub n. We know that the integer only have subgroup nz, and also nz is cyclic group, right? And also mu sub n has only subgroup mu sub a when a is divisor of n, or n is multiple of a, right? And also mu sub a is trivially cyclic group. So the end. Good job.